Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel. And as I've promised that I will be back with by maintaining a couple of examples related to the first order linear differential equations. So here I am. So in my last video I tried to discuss quite exhaustively the theory of this topic, the linear differential equations of first order, and how we obtain the integrating factor that is going to help in solving such kind of equation. We obtain that integrating factor in the light of exact differential equations. So everything was quite exhaustively it has been explained. So you can visit that video. You can find the link in the description box, and after that I suggest that you should approach on this video. Okay, so over here I just tried to maintain an example. You can see that the general form of the linear equation is it looks something like this. So such equations which are expressed in this form or can be expressed in this form, they are brought in the category of first order linear ODE. Okay, so let's try to solve a couple of examples here. The first one I have already written over here for you. You can see that here I can observe that the variables are representing the polar coordinates. It's quite apparent. So you see here R is behaving as my dependent variable and theta is behaving as an independent variable because it is satisfying this format. It is actually satisfying this format. Okay, so you can see that the function q of theta is cos squared theta and p of theta is tangent theta. So it is definitely satisfying the linear format. So R is the dependent variable and theta is independent variable here. So as we have discussed in the previous video, the integrating factor that is going to be multiplied entirely with this equation, I just named this equation number 1 for my A's. Okay, so over here my integrating factor mu of independent variable is said to be mu of theta, and it is so obtained with the help of this formula, right? So over here you can see that it can be obtained with exponential raised to the power, that is the integral of tangent theta d theta. All right, so it is giving me exponential raised to the power secant square theta. Okay, I'm extremely sorry. I've just written here the derivative of theta, that's the secant square theta. I'm sorry, it's actually the ln of sec theta. Okay, so it is actually this. Let me just write it properly. It is this. Okay, so the anti-log is going to cancel out the effect of logarithm here, so just secant theta is going to be left. Okay, so it is my secant square theta. All right, so this is what you say integrating factor. Now we are going to multiply this integrating factor entirely with this equation. Okay, so on multiplying the integrating factor entirely with this equation, we are going to get a stuff something like this. So it is secant theta dr by d theta plus r of sec theta tan theta equals to sec theta cos squared theta. Okay, so you can observe here that we know that secant is nothing but a reciprocal of your cosine, so you can just write like this. That's the preliminary of your trigonometry indeed. So on cancellation, simply give me cosine theta. All right, so this thing is equals to your cos theta. That's quite visible. So now you can use here the basic or the primary formula of the derivative of the product of two functions, which is expressed something like this. Okay, So over here, this thing is written in this form in an expanded way. So if I just close it in this form, how about that? So I'm going to close it. Okay, so it can be written something like this then. Or sec theta, alright? Because you know that this is u derivative v plus v derivative of u, which is sec theta tan theta. It's quite clear. So that's it. This is it. That's the stuff. So now what we do, we are going to integrate both sides with respect to our independent variable theta. Okay. So on integration, life is getting easier now. So on integration, while integrating both sides with respect to our theta, okay, we are going to get over here the derivative and the integration are going to cancel out each other's effect because they are anti of each other. Simply the function is going to be left, which is this, okay, and it is equals to integral of your cosine theta is sine theta plus some constant. All right, that's what we have just obtained, and in the question we were provided this condition as well. So if your theta is going to be pi by 4, then in that case the value of r is going to be 1. Okay, so we are going to substitute the value of r equals to 1 and theta equals to pi by 4 in this equation to get our c, and then whatever the value we get, we will substitute over here, and that is going to be our last equation. Okay, the solution, what you say. Okay, so on substituting the value of r equals to 1 and secant theta pi by 4 equals to sine of your pi by 4 plus some c. Okay, so we know that secant is nothing but a reciprocal of your cosine, so you can write this thing as 1 upon cos pi by 4 as well. So you are getting therefore under root 2 getting multiplied with 1 definitely give you under root 2, so I'm just writing it directly for you. So this is it, 1 upon under root 2 plus some constant. Let's continue here. So c is therefore going to be under root 2 minus 1 upon under root 2, alright? So on taking the LCM, you're getting this stuff, which is 1 upon under root 2. This is the value of your c, alright? So once when we have just obtained our c, we'll substitute over here. We will substitute, and we just name this as equation number 2, okay? So give the reference of your 2, equation number 2, and it's finally giving you sec theta equals to sine theta plus under root 1 upon under root 2, or reciprocal of root 2. So as r is said to be your dependent variable, so r is basically f of theta, right? So either you can stop your work exactly here, or if you further want to beautify your answer, you just form an equation keeping r as a subject, because f of theta is said to be the solution. So therefore, so you can write this thing in a way that r is equals to 1 upon sec theta getting multiplied with this whole, sine theta plus 1 upon under root 2. So this is indeed your cosine. So r is therefore cos theta times sine theta plus 1 upon under root 2. So this is said to be the final form in my view. Okay, so that's how you obtain the value of your r, which is said to be the solution of this beautiful linear equation expressed in the polar coordinate system in 2 dimensions. All right, now let's move on, see one more example.